welcome to today's CAE webinar featuring the MeshWorks engineering software platform. We have a great agenda today with a focus on powertrain design and simulation, including guest speakers, software demonstrations, and an overview of best practices using innovative tools for the automation of CAE. My name is John Gilness, and we look forward to presenting to you and also receiving your comments and feedback when we reach the Q&A session. At any time during the webinar, feel free to type in your questions in the text box area, and we'll answer as many questions as we can at the end of the presentation. Detroit Engineered Products, or DEP for short, is your host today and also the creators of the MeshWorks software platform. We are a 22-year-old company that has grown to about 500 engineers globally with technical centers in 6 countries, MeshWorks vendor partners in 15 countries, and our global headquarters in the Metro Detroit area here in Michigan. DEP is comprised of 4 groups, including our engineering consulting and analysis group, our product development team that helps OEMs, suppliers, and investors bring specialty products to market, such as our engine ion sensor for reduced emissions and improved fuel economy, our MeshWorks software division, and our staffing and contracting team. So without further delay, we hand the baton over to Raj.
Thank you, John. Thanks for the introduction about our company. DEP MeshWorks is a CAE-driven integrated platform for pre- and post-processing, and it also involves the rapid concept model generation for CAE and CAD. With all the parameterization and automation capabilities, MeshWorks also offers a lot of process automation, concept modeling, and CAD morphing tools. In fact, MeshWorks has enabled all the leading companies across the globe to transform their product development cycle, thereby saving a lot of time and money and get to the market much faster. So coming into MeshWorks 2020, it's a powerful tool which has the CAE parameterization capabilities, where you can completely parameterize your FEA and CFD models. The next technology is our bread and butter, where morphing comes into picture. With our morphing technology, we can give upfront design solutions for CAD and CAE models. With our design optimization capabilities, we will be providing models for multi-solvers. With one model being the startup, we can parameterize and generate a lot of DOE studies with the help of MeshWorks. MeshWorks also offers a process automation capability, which helps the user to automate their day-to-day work, and it helps to save 70 to 80% of their time. MeshWorks pre- and post-processing techniques are pretty robust, and they are top in class as we speak, comparing to the competition. You can see a lot of advanced tools and pre-existing automated process for the day-to-day work, and you can easily save like 30 to 40% of your time, which you currently spend with the competition tools. Recently, we have introduced our ConceptWorks tools. This is pretty much used in all the major OEMs to perform all the architectural and concept studies. And now the next slide is like we are trying to give a comparison with the current and the new trends using MeshWorks. As we all know, with the current trend, we need to depend on the CAD model to be available from where we'll start our performance assessments. But with a transformed process using MeshWorks, we can pretty much use our existing models to match with the new requirements by performing the conceptual and architectural design changes. And the get-go itself, we can perform all the CAE performance assessments. And by the end of your conceptual phase, you will pretty much have a 90% frozen design. Thereby, your detailed evaluation visual validation phases will be much easier, and we may not have repetitive iterations of interacting with the CAD team and again coming back to FEA kind of a back-to-back process. Gets completely eliminated by using MeshWorks. You can also see our modules in different stages of the product development cycle. As we speak, many of our customers have achieved like 30 to 40% of time saving in their product development cycle in various applications. Saying that, I'm passing it on to our Radha, wherein we can have a panelist speech about our tools.
Yeah. Yes, Raj. Thanks, Raj. I think we will reserve that towards the end of the presentation. Okay. Any of the feedback from the participants. So now we can right away go to the technical part of the presentation.
Yeah. Okay. So Paresh and Aditya, please take it forward. Thank you.
Sure. Thank you so much, Raj, for the introduction. So today we will be looking at our first demo, that is templatized meshing in MeshWorks, quality correction tools, and once we do meshing in MeshWorks, how the model becomes auto-parametric, meaning that when a user wants to optimize the model by changing the size and shape of a model, how quickly a user can do it in MeshWorks, and also how integrated modeling tool benefits in MeshWorks too. So our first demo is on the meshing. So here we see a mount bracket on the screen. Now we have a very nice tool that is called as an integrated modeler, where user just has to select the CAD components, as we can see on the screen, and then user has to select the templates. To select the template, we have given a specific path in the installation folder. We have given all the templates which are necessary to do the meshing. So now I'm selecting a 3mm template right here in front of us and simply click on execute. The mesh is ready. Now we can see very nicely all the fillets and the tubes are very nicely organized into a different collector as the feature has been identified. Now here, this is our main panel where all the templatized meshing inputs has been given. So the first one is general meshing parameters, where we give all the target element size, minimum size, and maximum size. So the first one is, that is 3mm is target element size. So we will quickly go ahead and see the element size as it shows 3mm. Then the second section of the measure control is feature identification. So features have been identified, as you can see on the screen, that a number of layers on the circumference are 24. And also we have given washer layer inputs as 2 layers. So as we can see on the screen, the tube has nicely been identified automatically through MeshWorks, and then 24 layers have been shown on the tube area or the tube circumferences. Then we have the fillet. So MeshWorks also very nicely identifies all the fillets in your model with respect to the given criteria. And as you can see on the screen, even if it is a very complicated structure, still MeshWorks goes ahead and identifies all the fillets. And not even that, it does a very good job while doing the meshing. Also, when there is a transition between a smaller radius to bigger radius or vice versa, it gives a very nice and smooth transition between the layers. So this was about the fillet radius. Now, again, we will go to measure control, and then we'll see how we can give an edge suppression if required, meshing process control parameter, and also we perform a quality correction. So MeshWorks goes one step further, and it not only gives the first cut mesh, but it also goes ahead one step further and does all the quality correction automatically for you. So user doesn't have to go back again to the quality correction panel and do the corrections again. So in this process, all the features have been nicely preserved. And then once the 2D mesh has been nicely created, it goes ahead and does the tetra meshing also. So be sure that the quality correction of a tetra mesh has also been taken place in the background. So that's how the tool very nicely works when it comes to meshing in MeshWorks. So automatically the tetra mesh has been created. And also we say that once the meshing has been done in MeshWorks, how the model becomes auto-parametric. So in my second video, I will quickly show you how the auto-parameterization works in MeshWorks. So we have a tool that is called as a casting. So on the left hand side, we see multiple parameters like fillet radius change, tube diameter change, rib height change, and rib thickness change. The first one is fillet radius change. So let's say a user has to increase or decrease the fillet radius, as we can see in the screen. So what a user has to do, he just has to select on the CAD curve. I'll quickly go ahead and play it. Yeah. Simply click on the CAD curve, define the deformable width and the percentage change, and simply a parameter is created. And now you can nicely see when I move the cursor from my upper bound to lower bound, how the fillet radius changes. Then we have a tube diameter change. So MeshWorks is smart enough to identify the tube, even if you have different single component for the entire tubes. And by just clicking on execute, the tube diameter has been created. And then you can see how nicely the washer layer has also been preserved when the tube diameter is changing. So once the rib height, now the third parameter is rib height change. So let's say if I have to increase the height of the rib, so I'll simply select the elements very quickly. So I have to preserve the fillets too, so that's why I'm selecting the fillets area. And now just by giving the range and the direction, and once I click on execute, a new parameter has been created. So as we can see, with no training or with less clicks of a button, we can create a parameterized model in MeshWorks. So this was our third parameter, that is wall height change. Now let's go ahead with the last parameter, that is rib thickness change. So this is a pretty difficult parameter to create. So MeshWorks can do automatically in MeshWorks by just clicking on the surfaces or the elements and giving the range and simply click on execute. A wall thickness has been created. A new parameter has been created. So I'll simply click on link and move my slider bar to my upper bound and lower bound. And now we can see how quickly we can see the wall thickness change. So this is a complete automatic procedure. When you do meshing in MeshWorks, user just has to come to this panel and simply click on the CAD surface or the elements, and then you can very nicely create a parametric model very quickly. Next is Hexa Meshing. So first we have seen how nicely and quickly we can create a tetra models or a 2D mesh model. Now we will see how very efficiently and quickly we can create Hexa Mesh for complicated structures like brake caliper, gear, splines, sprockets. So we will be seeing an example of a brake caliper here. So here we see a model that is nothing but a brake caliper. It is very complicated structure, and this is nothing but an outer skin of a caliper model. Now, as it is symmetric, we will have a cut section of it. And still, if you think so that the model is little complicated, what we can do is we can create different zones. So here we have treated the first zone as the green color, the second zone as the pink color, and then the third zone as the brown color, as we see on the screen. Now what we're going to do here is we will be taking the first zone and then we will create a core mesh, a core Hexa mesh from it. So MeshWorks has a nice tool where when you take the first zone, user just has to keep the model into a nice view where we can see all the features, and the features are nicely imprinted onto a CAD surface. So these are all the features. Once you imprint the CAD features, you just have to mesh it. Once the meshing is done, we have a nice tool that is called as an extruded hex mesh, parametric extruded hex mesh, which will take care of all the features in the model, and this would be your core output. As we can see, there are all sharp edges. So this is nothing but the core mesh output. It's not the final output yet. Similarly, we'll be doing it for zone 2. We will take the outer geometry, then we will identify the features, we will mesh the features, and then we will use our extruded hex mesh to create a nice core mesh. This was about the second zone. Similarly, we'll do it for the third zone too. And meanwhile, as we are doing it, we will nicely maintain the connectivity between the zone, first zone to second zone to third zone. Similarly, the mesh has been created. We can insert a washer layer also, and that 2D mesh will drive your Hexa mesh. So at the end, what we'll be doing is we'll be combining all our zones to create our core mesh. It's not a final mesh yet, a final Hexa mesh, but this is just a single core mesh. Now, as it is symmetric, we will go ahead and reflect our Hexa mesh so as to get our complete core mesh. And then we have a nice tool that is called as a hex mesher, where user has to select the outer geometry, and then user has to select the inner core, and it goes ahead one step further. That is called as a plastering technique, and it very nicely creates a smooth Hexa mesh, as you can see on the screen. So this is our final output. This is a semi-automatic tool where we can very nicely generate Hexa mesh for any complicated structures, as you can see. So now the next topic is an integrated modeler. So we will see how it is useful in integrated modeling when it comes for part replacement. So here we have a diff case assembly, as we can see on the screen. Now I will very nicely go ahead and just put it on a transparent view just to show that there are some bolt connections, and also there is contacts everywhere, which says that it is a runnable model and it has very nice node-to-node connections. It has all the contacts been created in the model. I will quickly go ahead and just display the diff case and click on Find Layer. So it will nicely show me the contact layer also, as you can see on the screen. Now, in part replacement, now what we can do is we will be importing our new model. So I'll just quickly go ahead, select my new model, click on Append. So this mesh is nothing but it will have a coarser mesh than the previous one, as we can see on the screen. I will quickly go ahead and simply show the actual model, my initial model. This is my initial assembly. Now I will click on reverse so as to see the difference between the initial assembly and the part which is going to replace it. So you can see that the red component is a coarse mesh, and also we can see a slot which has been there in the new mesh. This is kind of a new feature which we'll be replacing with. So in MeshWorks, we have a nice tool that is called as an integrated modeler. So I'll quickly go ahead and advanced mesh and integrated modeler, generate abacus model, wherein meshing attributes, user just has to select the current component. Here the current component is my green component, new component is my red component. Simply click on accept. Similarly, at the bottom, I will be selecting my green component as my current component and the blue as my new. So once you define the two paths, simply click on save. And once I click on generate abacus model, MeshWorks will very nicely identify the change. It will delete the old model. It will replace the old model's name with the new one. And not even that, it goes one step further where MeshWorks will automatically update the rigids, contacts, bolt connections, and at the end, we will have a runnable model. That's how the beauty of the tool is. It is very intelligent enough to identify all the changes and integrate into the new one. Similarly, we will be displaying the diff case assembly and simply click on find layer. This is how it preserves the contacts even if you do a part replacement. So this was all about from my side. Aditya, I will
Yes,
quickly
Paresh.
share.
Yeah.
Yeah,
Can you pass the baton
stop
to me?
sharing and sure.
Okay. Let me go ahead and share my screen. I hope everyone can hear me okay and see my screen. Paresh, if you can give me a confirmation that you can hear me and see the screen.
Yes, I can see your screen and hear you well.
Okay, okay. Thank you, Paresh. Thank you for the demos. So I will be moving forward with the next set of demos. We will look into how MeshWorks can enable design changes directly onto the mesh with no CAD needed whatsoever. So the first one that I'll be showing is the feature removal on a casting component, and the next one will be addition of ribs onto a casting component with wall thickness. And we'll also see how the strength and stiffness improvements, all these features are created without waiting for the CAD, and we can carry it out directly on the mesh level. For example, just say if the engineer wants to run topology optimization, we go through some of the steps, starting with removal of features, and then we create the design space, and then we run the topology. And from the result, the load path that we derive from the topology output, we can go ahead and create the ribs. So for the first demo, I will show you the feature removal. The prerequisite for defeaturing the ribs is going to be creating a shell or a 2D mesh over the feature. So as you can see, we have created a shell mesh. So once we have created the shell mesh, we go into the function of feature removal, and all the user has to do is to select the 2D mesh and simply click on remove feature. It will very quickly go ahead and defeature the ribs that we have selected. And once the user is satisfied with the output, he or she can simply go ahead and click on accept, and with just a push of a button, you can see how the user can quickly defeature such complicated ribs. So I can just go ahead and take a cross section to show you that it still is a casting component or a solid component. So this is the power and the efficiency of the function that MeshWorks hosts. So moving on to the next one will be the rib creation. So again, the prerequisite to create a solid rib, and this solid rib will be directly fused onto the base component. So the first prerequisite is to create a 2D mesh in the region where the user wants to create the tetra rib. So once we have created this, I'm just showing you that it is a solid component. So we can go into the advanced mesh, where we can go into the shell or tetrarib creation function. So our first input will be to select the contact zone. So this specifying where you want to create your tetrarib. And then the next input will be to define the plane. So we will select the nodes. We will select the nodes as to where we want to create the plane. So once we create the plane, we'll just click on execute. And once we are satisfied with the output, we can just click on return. So it will give us the reference nodes. So the next input will be to select the start and the end point of the tetrarib profile. So I'll go ahead and select the two reference nodes. So this will be my point A to point B. So once I've selected that, my next input will be to sketch the rib. So when I select the option, it will automatically show me the cross section of the reference nodes. So I will go ahead and select my reference nodes, and it will give me the profile of the tetrarib. So the user also has the power to modify the curve. The user can modify the curve with respect to the load path that we have got as the output from the topology result. So once the user is satisfied with the profile, we can simply go ahead and click on accept. So once we click on accept, we can go ahead and give the parameters for the tetrarib as our input, and then simply click on preview profile. So the user can specify the element size, the feature angle, the rib thickness, draft angle, even the number of layers in our fillet zones, etc. So we can just go ahead and click on create tetrarib, and in just a matter of seconds, you can see we have very nicely created a manufacturable tetrarib that is fused to the base component. So all this is done in few minutes without even getting the CAD from the CAD engineer. All this is done with just the base component, base tetra mesh that we have. So this is the power of the tool. It is very simple and very easy to learn this. Moving on to the next function will be the solid Boolean. So in the solid Boolean, we will first look at the non-intersection method, where we will select the base component and the slave component. So the slave component will get merged with the base component. So we will select the 2D face as the master and slave as well, and then simply go ahead and click on the merge option. So you can see how easily, not only that it's merged with the component, it's also put it in the same PID as the base component. So the next step will be the union process, where we have a shell part. So we would like to create a tetra mesh and again fuse it with the base component. So the inputs are similar to the previous one, where we go ahead and select the master and the slave component, and then the input for the 2D mesh, and then simply click on create a solid Boolean. So we can very easily go ahead and create it. So the next one is to create a slot in this particular region. So if we have a shell mesh and then a face mesh over your base component, your base cast component, solid component, just go ahead and select the master and slave, and simply click on the solid Boolean function. So very quickly, it will go ahead and defeature that area by creating the slot region. So the next function will be to retain all the sets in different PIDs, where just say we have an intersecting component, a feature like a rib, where we just select the base, the master and the slave, and then we can quickly go ahead and do the solid Boolean function by retaining all the features. If you can see, it's retained all the features and also put them in different PIDs. So moving on, after we have done all these functions for the model buildup, the next one will be to create connections. So I will show you one such example, which is the auto solid bolt connection. So we have a powertrain component here. We will use the auto bolt creation of MeshWorks to create auto solid bolts. I will go ahead and select the components where I want my bolt to be created. I will select my unthreaded part and define the diameter range. So within this diameter range, it will automatically go ahead and identify all the possible bolt locations. And you can see that it's highlighted certain bolt locations. By doing this, it will tell us which bolt locations come into contact with the two components that we have selected. So we can also go ahead and define the bolt, the solid bolt. The user also has the power to change the parameters like the shank length, head dia, or if you want a hex bolt or a tetra bolt and all those things. We can also create pretension layers. And once we have selected all this, given the inputs, just click on preview. You can see very quickly, within just a couple of seconds, we have created the bolts. Rest assured, if you have a block and a head of an engine assembly, and you want to create 12 bolts in one shot, it is also possible. You can select multiple components and create multiple bolts in just a click of a button. So you can see that we have created the hex bolt, and Meshworks not only creates the bolt automatically, you can see it creates the pretension surface as well, and it also creates the contacts. You can see that it's created contact surfaces with the washer and the component. So Meshworks is very efficient. You can also see, and in the threaded region, that it's created contact pairs. So just imagine when you work with an entire assembly, how much time this particular function can save you by creating the 3D bolts as well as your contacts also. So moving on to the next one, this is where we will be looking into battery modeling. So when it comes to battery modeling, here we can see the parts consist of variety of modeling techniques. We have shell mesh, we have tetra mesh models, we have hexa mesh models, and we also have to do the connectivity. The connectivity being seam welds, 1D bolts, 3D bolts, etc. And we as an engineer, we know such models are really complicated and it consumes a lot of time. We will now see how we can use Meshworks to very efficiently create such assemblies. So the first one is, how do we efficiently model battery cells? As you can see here, we have modeled the anode and cathode plate using the mesh template, and then we have covered it with a coolant plate, and the coolant plate is connected to the anode and cathode by using a 1D element connections like beams and rigids. And finally, we can stack up these anode and cathode plates to create the fuel cell. So these fuel cells can be integrated into a battery housing. So all of them can be created using mesh templates. And now I will show you in detail how we can go through the process from point A to point B. So coming to the next topic will be the electric motor. So this is where we go into the full detail of the process. Here we can see how the rotor stator and how we can connect all these models together. So the first one is, we have an assembly of a CAD model. In this, we have a couple of parts which have to be tetra mesh and some have to be hexa mesh parts. Now, when it comes to tetra meshing, it is as easy as a push of a button using Meshworks. So here the user can select the CAD data. So once the CAD data is selected, we can provide the mesh template, and it will take care of the element size and the feature conditions like fillets, tubes, and washers, etc. And also specify the quality parameters. Based on that, we get a very nice output with very minimal interaction from the user. So coming to the next topic, which will be hexa mesh creation. We have variety of functions, and in this example we will show you some functions. Here the tool will automatically identify the symmetrical path and give us the sector of a model, and it has been meshed as per the quality and the flow and replicated as we use a function called the parametric extrusion. Even though the model is having various depths, the tool will automatically segregate them and give us the output accordingly. So this is a very simple function. So normally, as you know, hexa mesh takes a lot of time. So we have this very good feature called the parametric extrusion, what Paresh had explained to us. So this is a very useful function. So we might have a lot of other intricate models in our design. So Meshworks can be used to create such models. Just like the previous example, we have the auto identification and segregation of a gear model. So we will have a gear model, and Meshworks will automatically go ahead and segregate it. And once it's aggregated, it will go ahead and mesh it. And with using the parametric extrusion, it will go ahead and create the hex mesh. And once we have created it, we can go ahead and fully rotate it in 360 degrees to recreate the full gear. So you can see in less than a few minutes, you will be able to get this output with just a section of the CAD, which is also done automatically using MeshWorks. So here, as we have seen some of the modeling in detail, what if we want to carry out some other techniques using complicated CAD? For example, the solenoid model or wire. Even though the CAD is detailed, we would like to create some simplified model for analysis purpose, which is also possible using MeshWorks. So the next one is, after creating the meshing, we need to assign the materials and properties to the model. So here in MeshWorks, we can use the assign bill of material function, wherein the materials and the properties are given through the CSV file and the bill of material is assigned. So it is a very quick method. So the next step will be to create connections through contacts, rigids, and bolts. So in this case, we can automatically create contacts using the auto contact creation function using MeshWorks. We have to simply go ahead and select the components where you want to create the contacts, and the function will automatically create the contacts with respect to the tolerance between the two components that the user has selected. So we also have the other type of contacts creation. For example, the 1D bolt creation. For example, if we have a Nastran model, MeshWorks will automatically go ahead and identify the bolt location, similar to the solid bolt that I just showed you. It will go ahead and create the rigids and also beams in the bolt location. So the final one being the solid bolt. So this is the same demo that I showed you, but I'm showing it to you on the motor stator rotor model. So you can see by just selecting the components, MeshWorks will automatically go ahead and create the bolts for us. So I've shown you the entire process, and Paresh also shown you some of the pre-processing models. So all this put together, you can see how MeshWorks is very efficient, and it's very it's time saving for the engineer. So this will be the end of my demo.